Our topic in Chapter 6 is once again revisiting tests about a single population mean, and we'll also discuss how to compare two population means for equality in this chapter, and that all of this is done in a new procedure to us, and that is the t-test procedure. We did see some capability in the univariate and means procedures for being able to test a single population mean, and so we'll investigate that instance or that type of test here again using t-test in addition to the comparison of two population means, whether the samples are independent of each other or dependent samples. So first, just some basic syntax for the t-test procedure is that there are other statements and options than are available in SAS help and documentation than those listed here, but this is our good introduction here. So within proc t-test, so that's not a typographical error, it is two T's, and data equals specify your data set name, and then we'll have proc t-test statement options. We have a class statement, a paired statement, and a variable statement or a VAR statement. I omitted in the list here the by and where statements, but they are of course again optional statements. Again, just remember with the by statement that you have a compatible sort having previously been done. So now we're never going to use all three of these statements in a single t-test procedure, but we'll look at some selections where there's only one or two of those statements used together. First, options we look at for the t-test procedure. We have the alpha option where we specify a probability given by P here, and so that if we want 95% confidence intervals, alpha is 0.05. That's actually the default setting. If we don't pick an alpha, typically we look at values of 0.1 and smaller for reasonable values of alpha. There is an opportunity to compute a confidence interval for this population standard deviation, and you can suppress that information. If we're looking for single population tests about the mean, or two population tests, we'll automatically get the confidence intervals for the means and the difference between the means in the default output. So if the 95% isn't the confidence level we need, we'll need to make the correct choice for alpha. Continuing on the next page of the book, H0 equals value, so this is where we can specify what value a single population mean is to be compared to. This is similar to the mu0 option in proc univariate, and remember in proc means we didn't have such an option. We can get some plots generated here, and they're listed here in things that we would like to see. Some of these may be restricted for only the paired t-tests, and we'll see some of these in the output, so you can control that list. An option that's newer in proc t-test is whether we're doing a one-sided test or a two-sided test, and we'll review those procedures here shortly. So you can write sides or sided or side, either one of those three versions of sides, and so you can have it's two-sided, it is lower test, or it's an upper test, and so that you can specify those, and that means you're also going to get a confidence generate an upper confidence or lower confidence bound, whichever is appropriate for the test you're doing. The class statement in this procedure is a bit different than the class statement that we saw before in the univariate means procedure. The class statement here identifies the variable that creates the two populations you wish to compare when you want to run an independent t-test. In proc univariate and proc means, it kind of worked like a by statement, didn't require a sort. That's not the case here. The class statement says which variable identifies the populations to be compared. Then the variable statement then is which response do you wish to compare for those populations. And then the paired statement is a standalone statement, and so whenever you have samples that are somehow linked or dependent, or referred to as paired, we need the paired statement to identify which responses we're going to compare. Okay, just a brief review of the hypothesis testing for a single population mean. Previously, the things that we did was for a two-sided test. That was the p-value generated for the test of the mean in the univariate procedure and also for the means procedure. And so that if you wish to specify mu equal to some specific value, we know that's done by t-test. If we have a two-sided test, we have a two-sided rejection region, and complementary to that, we can look at the confidence interval for mu. So our choice of alpha only impacts the size of the confidence interval. Our choice of alpha does not make a determination of what the magnitude of the test statistic will be. That's a function of data alone. We've also included a one-sided test here, and that was not included before since the output didn't generate those. And so this is saying that mu is specified is greater than some specified value. It's the same test statistic, right side test or upper side test, upper side rejection region. We actually are just basing things off of p-values, not rejection regions. And then the complement to this is a confidence lower bound, and so that we don't split the alpha up in determining this confidence limit. So it's only the lower bound then that we look for here. The opposite then for a left side test, left side rejection region, and a confidence upper bound. In this application, our degrees of freedom for the test statistics that we compute is equal to sample size minus 1 in this application. Emphasize that. To begin our objectives here, we'll look at the instruction data set that we have seen before, and where we have two programs designated as capital A and capital B, and then there's a performance score measured on participants in the program. And we can use the t-test procedure to test whether or not the mean score is equal to 75. So notice here the syntax for doing a single population test involves only the proc t-test statement and the variable statement. Title, of course, is optional, and we're labeling it. And then this h0 equals 75 is one of the options on the proc t-test statement. And so that if we submit this code, takes a little bit longer when I'm recording to run even the simplest of programs. Our output then, it's labeled by t-test procedure and for which response variable. So here we only had score, we could have had more. And then it gives us the summary information like we saw in the means procedure. Additionally, it gives us the confidence limit for the mean. So you can see that 79.6 repeating is the center of that confidence interval. It also gives us the confidence interval for the standard deviation. If we wrote CI equals none, it would suppress this. For the test statistic, it's printing here for us the value of t that I highlighted in table 6.2, and then the p-value associated with that two-sided test. So that if we were going to test this at alpha equals 0.01, 0.05, it'd be 0.05 if we've got our 95% confidence intervals. We would conclude then that the mean test score for students in these programs is different than 75, and then by inspection we can see here the 79.6 repeating is greater than 75, and so we could make the stronger statement there. We didn't ask for any graphics, but SAS has ODS graphics as support in some of the things we do. So we see a histogram of the scores, a superimposed normal curve is the blue curve here. Below this panel graph, we have a box plot of our scores, and then the confidence interval is the shaded green area here. And so this confidence interval is larger than 75, which is a little difficult to make out here, but that supports our decision to reject the null hypothesis. When we look at a QQ plot, we're looking for our data points to lie along this reference line to indicate that it's a normally distributed sample. In Objective 6.2, we're asked to produce 98% confidence intervals for the mean and standard deviation of the population of scores and test whether or not the mean score differs from 75 using alpha equals 0.02, and then turn off all of the graphs. And so plots equals none suppresses all of the graphs. The alpha, recall here, it's not going to impact the magnitude of the t-test, might change our decision, and we get 98% confidence intervals instead of 95% confidence intervals. So if we submit this code, much shorter since I don't have the graphics, we're seeing the QQ plot as the last image on the previous submission of this program, and so you can see the change in here at 98%. Of course, the t is going to stay the same and its p-value the same because those are functions of the data. Okay, now your decision may change, of course, depending upon the magnitude of your observed significance level. Okay, but the t-value itself and the p-value are functions of the data, and those are not alpha dependent. In Objective 6.3, we're to produce the one-sided tests for each program. Specifically, does the mean score for each program exceed 75? We'll suppress all our ODS graphics again and do this in a single t-test procedure. Okay, so now then we would need a by statement since we do this for each program. That's the function of the by statement. So we would have to have a sort done in a compatible manner in this program if it had not already been done. And then the variable we're analyzing is score. Plots again are suppressed. We're still looking at the hypothesized value of the mean is 75 and we're conducting the test at the 0.02 level, and we're also generating the 98% confidence intervals. What changes for us is sides equals upper, and so that whenever we look at the upper or right hand side of the test, then well, it's also going to impact our confidence limits. And so if we submit this code for Objective 6.3, it gives us program A up here at the top. Notice whenever you see that kind of delimiter that indicates a by statement was used. The summary statistics for those we have seen before, and so here program A does not differ or from 75, doesn't exceed 75 either. We notice the confidence lower bound, it is 70 to positive infinity, and that 70 is below 75, so that also supports our decision. The downside to the t-test is that it prints the t-value here, but it doesn't print what value we're comparing it to. I wish it did that. In the second part of this, it's for program B, and so program B scores are larger than 75. So this p-value is 0.0004. This is a one-sided test. The degrees of freedom change because the sample size is smaller, of course. You can see that this is a one-sided test when you look at the output because it's probability greater than t. If we look back at the two-sided test, it was probability greater than absolute t. And so if it were a left side test, we'd see probability less than t. Also for a right side test or upper test, then you see that this is just the lower bound and positive infinity for the mean. When we look at this before, two-sided, I have a confidence interval, not just a confidence lower bound. And so this confidence lower bound of 78.56, that is larger than 75, that supports our decision that says that the mean for program B is something larger than 75. Again, we use the by statement in the syntax here. We've seen a class statement before. It has a different implication in this procedure, so just proceed with caution. When we conducted these same tests for the combined programs for A and B, we did this in the univariate procedure. This was our resulting output, the student's t that's across here. So you recognize this 0.0072. That is in agreement with what we did That's the univariate procedure that agrees with what we have just done in t-test. So there's two different ways to do it. I like this one because it does tell me what the hypothesized value is. The limit with univariate, though, is it only does two-sided tests. And so here you also see those absolute value bars. These bottom two are non-parametric tests, and so you would need some background in a non-parametric statistics course to fully understand those. We're looking at parametric, meaning that there is a distribution associated with the test we're doing, and that's the normal distribution. That's a parametric test. When we cannot assume normality, we can look at non-parametric tests. We could do something similar in the means procedure as we've done in t-test and univariate, and for that you have to create a departure from that hypothesis value 75, because all that the means procedure does is test whether or not the mean is 0. So if it tests that the score minus 75 is different from 0, if it does that single computation, that's also what we're doing in the two-sided test. And so for the means procedure, you can look at score and score 75. So the confidence interval for score makes sense and agrees with our first t-test procedure. Our test statistic for score minus 75, notice this is 75 lower. Our dispersion is the same. All we did was move it over 75 units. Our t-test and p-value, those match the initial results from proc t-test, and they also match proc univariate for the two-sided test. There are two population tests that we can look at. The first is with dependent samples, so it's the idea of you measure before and after, something that happens like on twins. There's a lot of things with identical twins, somehow the data are linked to each other or paired. And so if you recall what we do in our beginning classes, we compute the difference across the pair and we compute the average difference. That value is this d bar, and then we look at the standard deviation of those differences and how many pairs do we have. And so as soon as we compute the differences, this looks much like what we're doing in a single population test. When we have independent samples, there's two different cases. One if the variances for the populations are equal, and one if the variances for the populations is different. And so we can look then, we compute the t-statistic where we use the pooled variance measure, and confidence intervals also use that pooled variance measure. Whenever we cannot assume equality, then if they're not equal, they're not pooled. Now each variance has a degrees of freedom attached to it, and so if I don't pool them, then what degrees of freedom do I use? And so I've labeled this as df star. And this information for df star here is the Satterthwaite approximation for the degrees of freedom, and so SAS does that computation for us. To know which test, the equal variance test or the not equal variance test that we should be doing, there is a hypothesis test for the equality of variances, and that is an F-test. And the details are given here, and we'll discuss those when we talk about independent populations or independent samples from two populations. To demonstrate the paired data t-test, we have a brief example here. Subjects are measured for improvement after receiving a treatment. Responses for each subject are given here in this table. Higher scores are the preferred or indicate improvement. So subject 1 had these two scores. So before, lower, high scores after. So generically indicates improvement. Some of the improvement is smaller than others. Some is quite large. So are we seeing an increase there that means treatment was effective, or are they just different just due to random variability alone? I'm not going to do anything with the comparison of the computation of the standard deviation confidence intervals. I am going to look at the confidence intervals for the population means and the paired statement before star after. So do you want to take this as before minus after? If you look at before minus after for the given kind of statement here, it's going to be a negative number. If you want after minus before, then it's after asterisk before. You can look at multiple pairs in a paired statement, and those are actually shown in an earlier table in your book. Which two variables are paired, and generically of those are A and B, and so back in table 6.1, the A star B, it's going to compute A minus B. And you can do more than one pair in here, and so there are 3 different syntax options to show you how those go. So for us, if we wanted A minus B, we listed as A asterisk B. If you want B minus A, then you need to reverse the order of those here in the paired statement. And that would happen with any of these different options for syntax. Alright, so if we take our code here and submit this, again is labeled the t-test procedure, and then it writes here before minus after, and as we thought we would see, we'd have a negative number. We can get a confidence interval for the mean difference. This one end is negative, one end is positive. Therefore, given the high variability in the scores here, would we conclude a difference at alpha equals 0.01? We would not, because 99% interval captures 0. Our p-value for this two-sided test is 0.02, bigger than 0.01. Therefore, we'd say that there is not a significant improvement at the 0.01 level. Again, there are some default graphics that are generated, so we see the histogram with the observed differences, very broad confidence interval in the background here in the green, captures 0. Paired profiles, so each of the before scores is connected with each of the after scores, so that if there were significant improvement, all of these lines would be would have a strong positive slope. The red line in here this is the before mean, and this is the after mean. You can also look at agreement plots when your data are paired. So this is the before mean and the after mean ordered pair, the 45-degree line here for reference, and so that we plot each of these. And so here we see the after and before are equal if they occur on this line. If they're all above, after is greater than before, but how much greater is what we're testing. We only had 5 pairs, so when we look at a QQ plot, we're looking at the normality, investigating that for our differences, and so that's a little hard to detect when you have only 5 data points. In Objective 6.5, we're just looking at different effects on the plots, and so you can look at the ODS graphics. If I only want the histogram with the box plot, I put only in there. We can always look at plots equals none. We can also generate those a box plot and the interval, and the shaded confidence interval, and look at a left-sided test here. So really what this is more about is that we can change the graphs or be more selective. So this is just the box plot with the interval in the background. In that second one, it's graphed out here. That mean difference, so that that gives us this interval, and that's associated with this left-sided test also. So when we have a left-sided test, we see less than t here. So this is the second run of that. The first one we asked for the histogram, and we asked for this interval to be done separately. So they were previously all a part of the same graph. That completes what we're going to talk about for dependent samples. Next we look at independent samples. And so we'll look at the SAS coding for this. We get the F-test that determines which of these cases we will use. We will see a T based on a pooled variance and a T based on an unequal variance, and it automatically computes both of those, and we'll see enough information to determine which of those is appropriate for us. In Objective 6.6, we are looking at an independent t-test. We are going back to our instruction data. So here for instruction, I have no modifications here, so I'm going to have 95% confidence intervals. I'm going to get confidence intervals for both mean and standard deviation, and I'm going to get all of the default ODS graphics that are available. Now, with regard to syntax, the class variable here operates differently than univariate and means, as we've said a few times already. This is the variable that identifies the two populations, and then we want to compare these two programs, their score response. If you have programs A, B, and C, then you will get an error that your class variable has too many levels. If you have typographical errors in your data, such as uppercase A, lowercase a kind of things, again, data are case sensitive, and you would again get that there's more than 2 levels for this variable. So there's an opportunity for you, or it identifies for you if you have a data entry error. So for us, then, if we run this information, it gives us a summary table again for each of the programs, and gives just the similar information like we get out of proc means. Difference 1 minus 2 with, and it says pooled or Satterthwaite. So are we using the S of P squared that was in the previous table, or are we using the individual variances and estimating the degrees of freedom, or computing that DF star value? So it gives us here the difference between those is it took A minus B. That's why that's negative. So since we didn't have a 1 and a 2, it's the first one minus the second one. And then it looks at the confidence intervals for each individual, the confidence interval for the difference. Now then, this part down here, the method here, these are the t-test methods. This is the f-test. So if we read the f-test here first, it's testing for the equality of variances. So this is the test up here, not the conclusion. For this for this p-value of 0.3527, that's larger than any reasonable alpha, so we would say that an equal variances test is appropriate. And then we read the line in this table here that says the variances are equal and what was the t-statistic. And so it does a two-sided test in this as well. Can you specify one-sided test? Certainly. So if we did want to run the left side test, or lower side, sided equals L is the only change I make, I'm still going to end up with all the graphics. Pardon me, this is 6.7 for our objective. Left side test, so it's looking at 1 minus 2, is that less than 0? And so we're getting a confidence lower bound for the, confidence upper bound for the difference. We are saying the equal variance assumption has been met. Notice that our p-value here says less than t, and these values are 1/2 of what we saw before. And so we would find that our means are different. In this one, our one mean is less than the other, significantly less than the other, or program A is less than program B. And then likewise, if you run the upper side, your p-value is still going to take A minus B. When you look at an upper sided test, probability greater than t, you'll notice this value takes 1 minus that previous p-value for the lower sided test, and that's because the probabilities must sum to 1. And so that you just want to be careful on those one-sided tests here that you don't have the control over A minus B like you do in the paired test, where you can specify the order. So just be attentive to what you're getting and look at does how the numbers are computed, and then make sure everything logically follows from your questions. All of the tests in this section were based on the assumption that the data are normally distributed. And so in the next chapter, we actually look at a case where I have two or more means or two means, and what if they are not normally distributed? How do I conduct that test? And then also we look at well, what if there are more than two means? How can I test for a difference among 3, 4, or more population means? And those are the topics in chapter 7.